Swayam Prabha. Digital India. Educated India.
Hello and welcome to this lecture on problem solving using DH parameters. In the last two classes, we looked at how to assign access to the various joints of a robotic system. And after we have assigned our access as per DH notations, then we make our DH parameter table. And after making our DH parameter table, we can make the transformation matrices which will take us from one frame to another frame. Okay, the objective being that we need to find the relationship between the end effector frame and that of the base frame. So today is problem solving, and today we'll solve a couple of problems, basically how to assign access and how to write the DH parameter table, because the more practice you do, the more familiar you become with the process. And then we'll look at a MATLAB exercise where we are going to enter a generalized matrix and see how we can find out the transformation matrix from the DH parameter table. Because as I said before, that in a robotic system where we have many degrees of freedom, it is not possible to do by hand. So we have to use a computer program like MATLAB to get the transformation matrices and then to find the relationship between the end effector and the base frame. So let's look at problem solving session today. So today we are looking at practice problems using DH parameters. So very quickly what I'll do is I will revise about DH parameters. I know I have revised it quite a few times in the last few classes, but I'll just very quickly go through what are DH parameters and then how do we assign our access, and then proceed with a few problems. So we have seen that in a three-dimensional case, when you have a linkage in 3D, so we have a shape something like this. Okay, it is having any three-dimensional shape, and we assign our access. So the first thing is, given a robotic mechanism, we have to assign our axis. Okay, and how do we assign our axis? The z-axis is the axis of rotation or translation. So this is my, let me change the color. So this is the axis of translations or rotations, and this I am going to call my z-axis. So this is zi minus 1, and then the other axis is here. Okay, so this is my zi axis. Okay, so we are assigning our z-axis is the axis of rotations or translations. Okay, so this is the first thing that we need to do. Next, what we do is we fix our x-axis, which is the shortest distance between the two frames. So my x-axis is going to be in this direction. If I say this is the shortest distance, then this is my xi minus 1, and this is my zi minus 1. Similarly, on this point, let us say this is my, okay, this is my xi, okay, and that's my zi. Okay, so now we have fixed our axis, and if we fixed our x-axis, x-axis is the shortest distance between z's. Okay, now if the z's are intersecting, then it is perpendicular to plane of z's. Okay, this is something we have seen. Now the point of this is we want to find how many transformations are required to take the frame zi minus the I minus 1th frame and align it with the ith frame. Okay, how many transformations are required? And it would appear that you need 6 transformations. Why 6? Because a rigid body in space has 6 degrees of freedom. Okay, but if you see closely, we don't need 6, we need only 4, and that is the beauty of the DH parameter system. So the first thing that we do is we make an axis which is parallel to this. So this becomes parallel to this, and we rotate this by an angle alpha. So I rotate my z-axis by an angle alpha. So the first transformation is alpha. Then I move. So my zi minus 1 has come here. Zi minus 1 has come here. Then I move it by a distance a. So if I move it by a distance a, what will happen is the zi minus 1 will go here now, and this is my xi minus 1. Okay. Now we see that the xi minus 1 and the xi's are not aligned. So what I do is I rotate xi minus 1 by an angle theta, okay, and align it with the xi. Now the xi minus 1 and the xi's are aligned, but the origins of the frame I minus 1 is here, and the origin of the frame I is here. So there is a distance. So what I do is I move this up by distance d. Okay. So what do we have? We have 4 parameters, A, alpha, D, and theta, and these are called the DH parameters. Okay. Now, if you want to go from one frame to another frame, what we can do is we can get a generalized matrix which is obtained by multiplying all these 4. So this is a rotation matrix. This is translation, this is rotation, this translation. All these 4 are 4 by 4 matrices. So if I write this 4 by 4 matrices, one for rotation, this one translation, then rotation, and then translation again, what I will get is a generalized matrix which is like this. So the generalized matrix T that comes out is equal to cos theta minus sin theta. So let me write a little further. Then we have 0, we have A, then we have sin theta cos alpha and cos theta sin alpha. Then we have minus sin alpha and minus sin alpha D, and here it is sin theta cos alpha, cos theta sin alpha, and here it is cos alpha, and the fourth one is cos alpha D. This is 0, 0, 0, 1. Okay, what is the use of this DH parameter table? The use of this is, what is the use of this generalized matrix? Is that in a computer program, what we can do is we can write the DH parameter table, which is a matrix, and then you take one row of the DH parameter table, put it into this matrix, and you'll get your respective transformation matrices. Okay, so we'll write a computer program at the end today and see how that can be done. But what we'll make use of is we're going to make use of this matrix, which is the generalized matrix. So this is the generalized matrix. Okay, so this is the matrix which is going to relate the I-1th frame to the ith frame, and we can put in the values of A alpha, D theta, which we are going to get from our DH parameter table. So our DH table will come like this: A alpha, D theta. These are the joints. So each of these rows will put in there and get the corresponding matrix 0 to 1. This one is going to be 1 to 2, and this is going to be 2 to 3. Okay, so please remember this matrix. We're going to use it. Now, before we go there and write a program, what we'll do is we'll assign our axis, okay, just for practice with a few problems, because unless you have a lot of practice, it's very easy to make it, you'll get confused, and it's very difficult to actually get to be able to do it for new kind of robotic systems. So what is the guidelines? Z-axis is axis of rotation or translation. X-axis is the shortest distance between the z's, or if the z's are intersecting, then it is perpendicular to plane of z's. So just these two rules we're going to use. Okay, so let's look at our first example. So this is our example number 1, which has a manipulator which is like this. So let's look at this manipulator, and our manipulator is like this. Okay, so this is a revolute joint and it has a prismatic joint. Okay, so if you can imagine, this is inside. Okay, so now what we can see is this is a 2 degree of freedom manipulator system. So this is 2 TOF. The first one is a rotating joint, so it can rotate like this. There is a theta. The second one is a translating joint, which can translate like this. So, okay, that is my D. Okay, so this is my D2. Okay, now where is D2 measured from? D2 is measured from here. So that's my D2, let's say. So this distance is my D2. Okay, so this is 2 DOF, and it has one revolute joint and one prismatic joint. Okay, now can we write the DH parameter table for this? Okay, let's write our DH parameter table for this. First, let us assign our axis. How do we assign our axis? Let me use red color. The Z axis is the axis of rotation. So this is my Z0 and Z1. Okay, then which is my X axis? Now you have to be a little bit careful here. Okay, in the sense that when you have a prismatic joint, you have to be a little bit careful about the X axis, because we want to find the distance between the axes. Okay, so Z0, Z1 is here. Now X0 and X1 is there. Okay, and for the second joint, this is my Z2 and this is my X2. Okay, So here we need to be a little careful because we have a prismatic joint here now. Okay, so now we have written our DH parameter table. Now also understand how this, when the manipulator moves, the first angle is a revolute joint, so it can rotate. The second angle is a translating joint, so it can translate. Okay, so my DH parameter table will be A alpha, D and theta. Okay, so this is my DH parameter table. Now Z0, Z1, X0, X1 are the same axis. So it is 0, 0, 0, theta 1, as is the case for a revolute joint. Now the second axis is a prismatic axis. So the Z1 and Z2 are intersecting. You can see that they are intersecting at a point. Okay, so if I draw it backwards, then it will intersect at this point. Okay, so what is the distance between them? There is no distance between them. What is the angle between them? So you can see that Z1 has become Z2 by rotating Z1 in an anti-clockwise direction. Okay, so this is an anti-clockwise direction. This has become 90. Okay, so Z1 has rotated anti-clockwise about the X, and it has become Z2. Now, what about the D? D is the distance between the X-axis. So here it is D2, and there is no theta, so this is 0. Okay, so now what we do is I can find out the transformation matrix 0 to 1. Now this is 0 to 1 matrix, and the other matrix is going to be 1 to 2. Now how do I find this? I simply take the first row and put it in the generalized matrix. So it is 0, 0, theta 1. Okay, so I just take this matrix and put it in here. So what would you get? It's a rotation about the z-axis. So you'll get cos theta 1 minus sin theta 1, sine minus cos. Okay, then 0, 0, 1. And all the translation between the origins are 0. So what will be this matrix? This is going to be cos 1 minus sine 1, sine 1, cos 1, 0, 0, 1, 0, 0. This is 0, 0, 0. This is 0, 0, 0, 1. Okay. How did I get it? I simply took row number 1 and put it in the generalized matrix. Now, what about row number 2? So row number 2, you see that there is an alpha there, D. So if you put it in the generalized matrix, what we'll get is 1, 0, 0. Okay, 0, 0, minus 1. Then we get 0, 1, 0. And we get 0 minus D2, 0 and 0, 0, 0, 1. This is what we get. Okay, so what we are getting is this, because there is a rotation of the z-axis by 90. So you look at the rotation matrix, what has happened. Okay, and there is the variable is d2 along the minus of the y-axis. So if you look at the y-axis, which direction is the y-axis? So y0 is this side. Okay, whereas x2 is going on the right side, and hence it is a minus on the y direction. Okay, so these two matrices we have got from our DH parameter table. Now what we'll need to do is we need to write a computer program which is going to take the numerical values of the rows of the DH parameter table, put it in the generalized matrix and get these matrices. Then we can multiply T01 into T12 and get the matrix T02. Okay, we can get it using MATLAB. Okay, this is what we'll do. Now before we go there, let us look at a few more examples where we'll try and see a few more mechanisms or robotic mechanisms where we are going to assign our DH parameters. So this is another robotic mechanism. Okay, so let's see, this is a robotic mechanism. Okay, so this is the base, and on this base we have a rotating joint. This can rotate, and inside this is a translating joint. Okay, so this is translating, and this translating fellow is here, and this is a translating joint. First thing is we need to understand how this joint moves. Okay, that's the first thing we need to do, is to try and understand how this is moving or what is moving where. So this is the other okay. So now what is the various axis? This is a rotating axis. It rotates like this. Okay, this is my base. Okay. So this second joint can rotate about the base. This one is a translating axis. So it is D2. This can translate So that's a translating axis. This is a D3. Okay, so this is also a translating axis. Okay, so we have theta 1. Okay, this base is fixed. I hope you can imagine this. So the joint 2 can go up and down, and the joint 3 can also move up and down. Now we have to assign our DH parameter. We have to assign our axis first. So how do we assign our axis? Let's say I fix my axis here. I fix my axis here and say this is my Z0 and Z1. Okay, where is X0, X1? X0, X1 is perpendicular out like this, X0, X1. Okay. So when this rotates, what happens? The angle between the X0 and the X1 changes. Now, where is the second one? The second joint is here, let's say. This is my second joint. Okay, so this is my, where is the Z2? Z2 can go up and down, so that's my Z2. And where is X2? X2 is this side. That's X2. What about the 3? So this is my Z3, which is this side. Okay, this is a translating axis, please note. So they are along the axis. Then X3 is this side. Okay. So now we can write our DH parameter table. So this is another problem. Now DH table. So the Z0, Z1 is the axis of rotation. Then X2 is translation axis in the same direction. Z3 is perpendicular to Z2. Okay, so that's correct. Okay, so now let's write our DH parameter table: A, alpha, D, and theta. So we have 3 joints, 1, 2, 3. 3 joints are there. Okay, what is the structure of this manipulator? It's revolute, prismatic, prismatic. Okay. So now the first one obviously is a revolute joint. So the first terms are always the same, 0, 0, theta 1. Now what about the second one? The second is a prismatic axis. Okay, and the z's are in the same direction. They are the same axis, so there is no distance between them. And Z1 and Z2 are the same axis, so there is no angle between them also. So it's 0. What is the variable? It is D2. So when this axis moves, what would happen is the distance between x1 and x2 will increase or decrease. That is the variable D2, which is coming here, and that's my 0. Then we move to axis 3. Now if you look at Z2 and Z3, Z2 and Z3 are intersecting axis. Okay, so if I extend it like this, they're going to intersect at that point. Okay, so they're intersecting, so there is no angle between, they are intersecting axis. Okay, so there is no distance between them. Now Z2 has rotated clockwise about x2, so it has rotated like this clockwise about x2 and becomes Z3. So this is a minus 90 here. Okay, and then what is the distance between the x? So when the third axis moves, the distance between x2 and x3 will change, and that is my D3 here, and there is no theta, so it's 0. Okay, so this is the manipulator which we are making. This is the third example I took. Okay, or the second example we had today, where we have RPP manipulator structure, and this is the way we make our DH parameter table. You need a lot of practice. Once you get the hang of doing this, it's very easy. It's not difficult actually. Now let's look at another example before we proceed further. So let's look at this example of, let me draw another manipulator here. So this is another manipulator. All these manipulators have different structures, and hence they are a little different. Okay, for example, here this is another one which can rotate about this joint. Okay, so we have sorry. Okay, this can rotate. Here is the base frame which is fixed. Now this one has a rotating joint here. So the rotating joint is having this one arm, the second one, and there is an end effector at the end there. Okay, so what are the 3 axes? The first axis is this one, so it can rotate about that axis. Is my theta 1. Then there is an axis here, which is my theta 2. Then there's an axis there, which is theta 3. Okay, and the last axis is here. okay, which is theta 4. Okay, now what is the length? This is L2, this is L3. Let us assume that the first axis, 0 axis, first axis and second axis are the same axis. Let's make that assumption. Now let us assign our z-axis. Z-axis is here, so z-axis, sorry, z0 and z1 are the same axis. So z0 and z1 are the same axis. Now, which is rotating like this. Okay. Now, where is z2? Z2 is in this direction. Okay, so this is my z2. Z3 is here, and z4 is there. Okay. So we have assigned our 4 axis. This is a 4R, 4 DOF, 4R robot. Okay, we are making the assumption that the first two axes, first 0 and 1 are the same, 1 and 2 are the same point. Now let's write our DH parameter table, A alpha, D and theta. Okay, before that we have to assign our x-axis. I did not assign my x anywhere. Okay, so we need to assign the x-axis. So where is the x0 and x1? So we can assign x0 and x1 like this. So this is my x0, x1. x2 is here, x3 is there, and x4 is that same. Okay, so now the first axis is the relation between the first frame and the 0th frame. So z0 and z1 are the same axis, x0 and x1 are the same axis. So this is 0, 0, 0, theta 1 is the variable, right? Now what about the second one? Now the second one we can see is that they are intersecting again. So z2 and z1 are intersecting at a point, although they are orthogonal, but they are intersecting. So there is no distance between them. Okay, but they are intersecting. So z1 is rotated anticlockwise about x0 by 90 degrees, and it becomes z2, right? So this is 90 degrees because the rotation is like this. Okay, then what is the distance between the x-axis? They are intersecting, so there is no distance between the x-axis. And what is the variable? It is theta 2. Okay. Now, what about the, so this is the second one. What are the third one? So the third one, again, the z2 and z3 are, if you look at them, they are parallel, right? So the distance between them is L2. Okay, and what is the angle between them? It's 0. What is the distance between x-axis? It is 0. What is the angle? It is theta 3 is the angle between the x-axis. What about the fourth axis? Now the z4 and the z3 are having a distance of L3. The angle alpha between them, they are parallel, so there is no angle between them. What about distance between them? Now distance between x-axis, they are intersecting, so there is no distance between them. And what is the variable? It is L4. Okay, so this is another manipulator where we have made the DH parameter table, and we are seeing that what the DH parameter table looks like. Okay, this is for practice. You could draw the manipulator by yourself, and you should put the x-axis, z-axis, then make your DH parameter table and see. So what I'll do from here is I'll first enter in MATLAB. I'm going to enter this generalized matrix, and in this generalized matrix we're going to take one row from the DH parameter table, put it in the generalized matrix, and get the transformation matrices. And then we're going to multiply all these matrices and get the combined transformation matrix, which will take me from the end effector frame to the base frame. Okay, so let's look at the problem. Which problem are we going to see? We'll see this problem. Okay, now in this problem, what we're going to do is, you can see that there are 4 variables in the DH parameter table. Okay, we had solved just some time back. Let's say I use the variable name t for theta, d remains as d, al remains as alpha. Okay, so alpha is al, a remains as a. So I'll write a generalized program in which I want to put a, alpha, d, and theta in this generalized matrix, and then take one row from the. So what I will do is I will take one row from here, and I will find out the transformation matrices. Okay, so let's go to MATLAB and see how to enter the generalized matrix. So the first thing that we are doing is we are writing our variables t theta equal to, let's say, 0 degrees, okay, just for example. Then we have theta, then we have alpha equal to 0 degrees. Then we have a equal to 0 for the first joint, and so t alpha a, and what was the other variable? D is also equal to 0 for the first variable, okay, for the first row. So now what we're going to do is we are going to find, okay, let me just put this as 30 just to show you how it works. Next, I have to input my transformation matrix T. Okay, so the transformation matrix T is equal to the matrix, the first term is cos theta minus sin theta, so I'm going to write cos D into T, okay, minus sin D into T, okay, then it is 0, then it is A, that's the first row. Okay, what is the second row? The second row is sin D into T multiplied by cos D into alpha, so that's the first term. What is the second term? The second term, cos theta, is equal to cos D into T into cos D into alpha. Okay, the second term. What is the third term? Third term is minus sin D into alpha, which is AL. So this is my third term. Okay, what is the fourth term? It is minus sin D into alpha into D. So into D. Okay, so this is my second row. What about the third row? It is sin D into theta, which is T, multiplied by sin D into alpha, which is AL. So this is the first term. Second term is cos theta, cos D into theta, multiplied by sin D into alpha. Okay, then it is cos alpha. Okay, and then finally it is cos D alpha into D. So this is the third row, and the fourth one is very simple: 0, 0, 0, and 1. Okay, so that is closing the bracket. Okay, so this one closes the bracket and gives us the, let us just check it once, because if there is any mistake, then it's very important that, so it is all D, cos D, sin D, sin D, cos D. So all D's are there, indicating it is in decimals. Sorry, it is in degrees. Sin D, cos D, sin D. Oh, there is a cos D missing here. It's a cos D, cos alpha, and then cos D into AL into D. Okay, so the other thing we need to note is that if the multiplication sign is all there. Okay, so now I can say that I have entered the generalized matrix. Now what I'll do is I will take the matrix, let's call this matrix T1. So this matrix T I want to compute. Okay, so this matrix T is equal to what? So this is my matrix T. Now let's just run it and see what it does. Okay. So see what it has done is it has given me two matrices, which I should have suppressed this one. This is also printing, so I will just suppress it. Okay. Now look on the right hand side. Your theta is 30 degrees. So it is cos theta minus sin theta. Okay, so it is cos theta minus sin theta, which you are getting 0.86 minus 0.5. Then it is 0.5, 0.86, 0, 0, 1. And here A and D are 0. So look at the DH parameter table here. Theta was equal to 30. AL, the link length is 0. AL is the alpha, angle is 0. A is the link length is 0. Offset is 0. So in that case, your rotation matrix is this one. Okay. So this is what we have done. Now what I will do is, let me call this as the matrix T1. So T1 is equal to T. Okay. So okay. T1 is equal to the matrix T. Okay, now if I run it again, what you see is we're going to get the matrix T1 as this. It has been assigned to T. Now what I'm going to do is I will go back here and try and explain what I'm trying to do. What I will do is I've taken the first row 0, 0, 0, theta 1, and I'm getting the matrix T1. This is what I've done here. Okay, so theta 1 is 30 here, numerical value. Okay, now the moment I put theta 1 equal to 0, I'll put theta 1 equal to 0 here. I put theta 1 equal to 0, and now I run it again, and what you get is theta 1 equal to 0. So you get the rotation matrix as an identity matrix, and this is 0, 0, 0, 1. Now what is the meaning of theta 1 equal to 0 here? Okay, if I draw it, it means that this is like this. Okay, theta 1 equal to 0, and the second link is there. That's what it means, right? Theta 1 equal corresponding to theta 1 equal to 0 degrees. Okay, so let me, okay, now what is the direction of x, y, and z? Let me draw it again. I'll only draw the zeros so that you understand more clearly. Okay, so in this configuration, where is the x, y, and z? So x, your z0 is this side, okay, x0 is that side, and y0 is this side, right? Okay, so, and this is my d2, theta 1 is equal to 0. Now if I take matrix 2, I want to find matrix 2 next. So what I'll do is I'll take this DH parameter table and put it there. So what is that equal to? And let me say d2 is equal to a length, let's say is equal to 10 meters. Okay, so I'll put 0, 90, 10, and 0. So let us go back to our MATLAB program and change it here. So the second row that I'm going to put there is theta is not there, it's a 0. The AL alpha is 90, so I'm putting 90 there. Okay, then A, the link length is not there, it's 0 again, and D is equal to 10. Okay, so now I'm going to put this in, and I'm going to say that T2, this is my T2 is equal to this number. Okay, so now if I run it, you'll get the matrix T2. Okay, so this is the matrix T2. Okay, so you can see that what has happened is that your rotation matrix has become 1, 0, 0, 0, 0, minus 1, 0, 1, 0, and 0, minus 10, 0. Okay, is it correct? When we wrote here, what did I write? You look at this, both the matrices in, well, you can see both of them together here. Okay, look at this matrix and look at this matrix. Okay, they are the same matrix. Okay, D2 only I have put a number which has become 10. Now, this means that using the generalized matrix and putting a row, I'm able to get the first transformation matrix, then I'm getting the second transformation matrix. Now what we can do is we can also multiply T1 into T2. Okay, so this is something we can do. T1 is for the first one, T2 is for the second one, and what we are getting, the answer is this one. Okay, so if you remember T1 and T2, T1 was the matrix for the first case, it was this one. T2 is the matrix for the second case, which is this one. Okay, and if I multiply T1 into T2, I get the answer as 1, 0, 0, 0, 0, minus 1, 0, 1, 0, 0, 0, 0, and here it is 0, minus 10, 0, 1. Now what I want you to do is to see this matrix, to compare, okay, to compare this matrix with the figure here. That's what we're trying to do. Okay, so if D2 is equal to 10 and theta 1 is equal to 0, then where is this one? It is in the y direction, it is in minus y by 10, and that is what you're getting here. Okay, so if you look at the, so the rotation matrix is simply give you the orientation of the frame. You look at the fourth column of it, it is 0, minus 10, 0, 1. So 0 means there is no difference in the x direction. There is no displacement in the x direction. This is the point P. The second term means minus 10 means it has moved in the y direction by minus 10. So if this is your plus y, this is your minus y, so it is minus 10 this side. And z again, there is no difference in the z direction, so z is 0 again. Okay, so this is how you can use MATLAB. This is a very primitive way of doing things. Okay, but I just wanted to show that we can write the generalized matrix like this. Take one row of the DH parameter table, put it in here, get the matrix, and we can do this for say 6 degree of freedom, 10 degree of freedom, multiply them all out and you'll get your final matrix. Now, as I said, this is a very primitive way of doing things, okay, just to give you an understanding of how it works. But a better way of doing things would be to write the DH parameter table itself. So if you look at the DH parameter table here, this is the matrix itself. And what you can do is you can take each row of the matrix, put it into that and get your corresponding matrix. So what you're dealing with are matrices now. Okay, so as we finish our forward kinematics, inverse kinematics, we'll look at a little bit more complex way of writing programs in which what we'll do is we will treat the DH parameter table also as a matrix. Okay, and each time we'll be taking one row, putting it into this, getting the corresponding matrix, multiplying them out, and then understanding how it works. So today was very briefly to explain how we can write the generalized matrix in MATLAB, take one row from the DH parameter table, put it into that generalized matrix and get the corresponding transformation matrix. And after that, what you do is multiply all the transformation matrices and get the relation between the end effector frame and the base frame. Now, after we finish the next couple of classes, we'll be seeing a better way of writing it. This is a very primitive way of writing programs, where the DH parameter table is also a matrix. We'll simply call one row of the matrix at a time and then find out and then derive the corresponding matrices, which will take us from one frame to the next frame. So today we'll stop here. So we'll stop. Thank you.